All right, so we've been talking about the logistic equation, and the logistic equation was great for as a population model when we were looking at situations where populations had a carrying capacity. Um, and we saw that from the slope field, as well as the solutions themselves, uh, that this behaved the way we would expect it to in this very simple model. Remember, we're focusing on the first quadrant as representing time starting at 0 and moving forward, and these would be our initial values, the amount of population we started with. And the slope field demonstrates the fact that if you start with a population below the carrying capacity and move forward in time, that the population will rise to the stable equilibrium solution of the carrying capacity, which is 4 in this case. Likewise, if you start with more and move forward in time, we get we decrease in population until we reach that equilibrium, that stable equilibrium. Again, not that we would ever do this, but if we ever start with a negative population, it doesn't make any sense, but we can see the population continues to decrease, whatever that means. It doesn't make any sense, but that's our logistic equation. All right, now, so we start with that, and if we're trying to model populations, we obviously have other considerations that can lead to different kinds of models that deal with different kinds of situations. So the last situation we'll consider is, suppose we have this population that lives on this island, this population of rabbits that lives on this island with a carrying capacity of M, and we are going to be harvesting these rabbits. Okay, so we're going to be, hunting them and using them for food, or selling them to kids for pets or whatever. But we're going to be removing them at a constant rate. All right. So that's the thing, right? So you can imagine this kind of situation, right? So we're adding another component to our model, and it turns out that if this is the model, if this is the the situation we're trying to model, we can still use the logistic equation, but we just subtract h, right? All right, so we're just subtracting h. That's how many per year are removed. So the population is decreasing by that many per year. All right. Now, what if we take a look back at our logistic model right here, we see that we end up with a quadratic, right? A quadratic that's missing a constant term. But with the harvesting model, when you subtract an h, you get your constant term back in there. So in essence, we're looking at our models will look something like this: ax minus bx squared. I'm changing some things around to make it simpler, right? This would be our km, and this would be m, but we're making our lives easier. So we've got a quadratic, right? Again, a quadratic. And our critical values, this is a quadratic, the critical values are the same thing. They are, what makes this thing, this right hand side, equals 0, and these are going to be either our stable or unstable solutions. And of course, since it's a quadratic, we know we can solve every single quadratic by factoring sometimes, but we can certainly use the quadratic formula. So we're good to find all of these. Now, we don't go into this idea, but we know that quadratic equations, they're going to either have 0 real solutions, 1 real solution, or 2 real solutions. And the number of real solutions depends on the coefficients, a, b, and h, I guess, in this case. And so when we switch from 0 solutions to 1 solution, or from 1 solution to 2 solutions, those represent some bifurcation points. We don't get into that, but if you want to read the last, third or quarter of this section, it talks about those points at which we switch from having 0 solutions to 1 solution to 2 solutions. as being our bifurcation points. We don't look at that. So we're just going to look at the situation where we have two solutions pretty much. So let's look at this equation. So 7x minus x squared minus 10. And so if we quickly try to find the critical points in order to identify not solutions, right? Because our critical points represent constant solutions, but they also represent these either these spouts or the funnels, right? And this one I think we can factor. Well, let's do it this way, right? Let's hit everything with a negative. So this is x squared minus 7x plus 10. Make our factoring life a little easier. So x minus 5, x minus 2 equals 0. So x equals 5 and x equals 2. All right. So there we go. Those should be solutions. They will be solutions. They are solutions. They should also represent equilibrium solutions, spouts or funnels on the slope in the slope field. So let's take a look. Let's graph this. Remember this? Remember we have to translate this into graphing notation. dy dx equals 7y minus y squared minus 10. So our graph understands, so our software understands it, and that's going to be what we enter into our nice little applet here. Okay, so we can do that. So we enter 7y minus y squared minus 10. Don't go there. There. Right? And we hit enter there. Okay, so let's take a look. Remember, focus on this right here. Focus on the first quadrant. This point represents our initial population. So, okay. So notice right away we have equilibrium solutions at 5, 2, and 5. And it looks like 5 is a stable solution because look, all our curves approach it as time goes to infinity regardless of where we're starting, right? All our solutions get sucked into y equals 5. Let's see, what is that? Y equals 2 is a spout, right? Our solutions move away from that, okay? Now, look what happens. If we start anywhere in here, our population increases until it hits its carrying capacity of 5. Okay, if you go back and look at the math on that, there's our carrying capacity is going to be 5. And again here, carrying capacity of 5, right? So if we start more than that, then our carrying capacity is 5. Now you might wonder about the 5. We'll talk about that here in a second. But there it is. Okay. Okay, now what's interesting is, remember, we're harvesting from this. We're taking out some rabbits every year. And so as long as we start above 2, then we rise and we're not taking out more than we're gaining. Okay? Right? Because they're reproducing more than we're taking out. As long as we start in this area above 2. Now if we start at 2, notice the solution curve kind of disappears, but really what's happening is we get the y equals 2 as the solution, right? GeoGebra doesn't pick that up, but we get the constant. So if we start out with 2, then we stay at 2. In other words, they have as many rabbits as we harvest, as we take off to sell, if you want a less violent image. Okay. Now, if we start less than 2, though, look what happens. They're reproducing, and we're harvesting, but we're harvesting faster than they can reproduce. So their population goes to 0. Okay, so this behaves the way we would expect. If we're going to harvest rabbits from this population, we would expect that has a carrying capacity. That's important. We would expect that as long as we don't take more rabbits out of the population than they produce, we we'll be fine. We'll reach a sustainable equilibrium of rabbits at 5, and we'll be good to go. But if we ever, start with less and harvest more than they reproduce, then we're not in good shape. So if we go back here to our equation, we can see what our carrying capacity is just by kind of grouping these two terms together to match the logistic piece. So if you factor out a y, you get 7 minus y minus 10. So looks like the carrying capacity is 7. That's the most they can have, and we're harvesting. We're taking out 10. So combined with their growth rate, we're able to maintain that. Now those numbers don't always work quite that nice, but that's the idea, and the idea is mostly expressed here, that as long as you start with more than 2, you can harvest yours out and you'll still be fine. But if you ever start with 2, less than 2, then you'll run the population into the ground. Okay, I will just mention this, and this goes for the logistic equation as well. This equation right here, let's get that right. Yeah, so this equation right here has a solution that we can find using our techniques. And I guess I'll do it for posterity. The solution is going to be this. Well, I should say this. Let me back up. If we can factor this into k times n minus x x minus h, okay. If you can factor it into those two factors with n and h being right there, then the solution, and I just mentioned this because sometimes you just need the solution and you don't want to go through the whole process of finding it. The solution is this: n times your initial x minus h minus h times your initial x minus n times e raised to the negative k n minus h t, all over, kind of ugly, the initial x minus h minus x, the initial x minus n, e to the minus k n minus h t, right? And so there it is. Okay, so that's the general solution to an equation that looks like that, a harvesting logistic equation.